This video will outline orders of reaction and how we use orders of reaction to write a rate expression. So let's start with orders of reaction. These tell us about how the concentration of a reactant affects the rate of reaction. And the only way we can determine the orders of reaction is experimentally. As we'll see in following videos in this playlist, they provide important information about possible mechanisms in a reaction. Let's have a look at some examples. In this example, let's consider a chemical reaction with three reactants, A, B and C, reacting together to form D. I've collected some data where I've independently changed the concentration of A and measured the rate of reaction. I've independently changed the concentration of B and done the same, and then repeated also with C. Let's first take a look at the data from changing the concentration of A and consider how that has affected the rate of reaction. In order to identify how changing the concentration of A affects the rate, I'm going to choose two experiments from this data table and consider how the concentration of A has changed. Let's take experiment 1 and 2. Well, if I look at the concentration of A, it has changed by a factor of 2. And looking at the rate values, I see that it's also changed by a factor of 2. So doubling the concentration of A leads to a doubling of the rate. So it looks like the rate is proportional to the concentration of A. Let's double check by comparing two other experiments in my table of data. Let's take experiments 5 and 6. Again, I see that by doubling the concentration of A from 0.08 to 0.16, I see a proportional impact on the rate. It also doubles. Let's see if we still have a proportional increase in rate if I triple the concentration of A. In this case, I could look at experiment 2 and 4. Here I can see that the concentration of A has tripled, and again we see a proportional effect on the rate of reaction, where the rate is affected by the same factor when the concentration of A is changed. For reasons that we'll see shortly, I can also express this change in rate as the factor by which A has changed to the power of 1. And you'll see why we did this in a moment. To summarise for reactant A, we can say that the rate of reaction is proportional to the concentration of A. And mathematically speaking, if I see a proportional sign, I can replace it by equals and a constant, something like this. Because changes in rate are proportional to changes in the concentration of A, I'm going to put an exponent of a little 1, meaning that the order of reaction with respect to A is 1, or it is a first order reactant. Let's now take a look at the data for reactant B. So let's consider how changing the concentration of B affects the rate. And in this case, we might choose experiments 1 and 2, where the concentration of B is doubling. And I might notice here that the initial rate has actually quadrupled. So by changing the concentration of B by a factor of 2, the rate has increased by a factor of 4, which you might notice is actually 2 squared. Let's perhaps compare experiments 1 and 3. In this case, my concentration of B has gone up by a factor of 4, and my rate has gone up by a factor of 16. Again, you might notice that the rate has increased by the factor squared by which the concentration of B has changed. So for reactant B, it looks like the rate is proportional to the concentration of B to the power of 2. Again, I can change that proportional sign to an equals and adding a constant. And in this example, because rate is proportional to b squared, we would say that the order of reaction with respect to reactant B is 2, or I could say it is a second order reactant. Finally, let's have a look at reactant C. Again, let's look at experiments 1 and 2 and see how that concentration change is affecting the rate. Well, the concentration is doubling, but actually there is no impact on my rate of reaction. And with a quick glance at the other rates of reaction, I can actually see that changing the concentration of reactant C has no impact on the initial rate of reaction. So the impact on the rate is the same as taking the factor by which I'm changing the concentration to the power of 0, which is always going to give 1. So as with the previous examples, I could express this as rate being proportional to the concentration of C to the power of 0. And I can adapt this mathematically, as we've already seen. Once I have identified the coefficient, I can then describe the order of reaction with respect to this reactant, in this case 0. Finally, we can consolidate the information that we have identified from our data in something called a rate expression. So let's quickly recap the information we've identified so far. The order of reaction with respect to A was 1, with respect to B was 2, and with respect to C was 0. I can now combine these three rate expressions, referring to each of my reactants, in one overall rate expression for my reaction. It's going to look something like this. Because the concentration of C to the power of 0 will always be 1, we might actually remove that from the rate expression because it doesn't change anything. And the coefficient of 1 next to the concentration of A also could be removed because it is simply the concentration of A. So if we are given a rate expression, it's useful because we can identify the order of reaction with respect to, in this case, A, B, and C. We can also use it to calculate the rate if we are given the other data, and we can also use it to calculate the rate constant, K. And you'll see more about those things in other videos. In theory, orders of reaction do not have to be integers, but in the IB we will only ever see examples of 0 order, 1st order, or 2nd order reactants. Hopefully this video was of some help.